class, welcome back to CSC 143, Introduction to Data Structures. We are looking at the second half of Chapter 12 from Building Java Programs on Advanced Recursion. That's sections 12.5 and 12.6. And just as a brief reminder, we had a previous video that covered the basics of recursion, and this is focusing on the advanced topics of recursive backtracking and an example of the prefix evaluator. I've just got a simple paint program here to show you the problem in section 12.5 recursive backtracking. It's called traveling northeast. So basically you've got a grid of locations here. You want to travel from the origin to some point determined by an x and a y. So if x and y are 1, 1, for example, there's really only there's two ways to get there. You can either travel east and then north, or you can travel north and then east. And those are the only two, or actually, sorry, there's a third way. You can travel northeast. So they allow you to travel north and east or northeast. So those are three different ways you can travel to 1, 1. It becomes more complicated when you want to go to something like x equals 1, y equals 2 here. So in order to get there traveling either north, east, or northeast, let's see how many ways we can find. So we can go, let's try to do it somewhat logically. Let's try going north first. So north, north, east. That's one. We can go north. It's terrible drawing. North, then northeast. That's 2. Then we can go try east, north, north. That's 3. We can try going northeast, north. That's 4. Or we can try going north, east, north. That's 5 different ways we can get there. So it gets complicated pretty quick. Let's think about how we can do this programmatically instead. So this type of recursion problem is going to work differently than our simple recursion problems. Remember, the simple recursion problems, we came up with a base case like n equals 0, and maybe we just had to return 1. And then we came up with a recursive case where we had to do something for level 2, for example. Maybe we multiply by 2, and then we multiply that by whatever the value of level 1 is. In these cases, we're actually going to be kind of going forward, going the opposite direction. So the base case here, if you think about how I just did this, the base case is when I reach my goal, right? When I reach my goal, that's the success. So whatever way I picked, once I reached 1, 2, I'm done, okay? There's also a case that I didn't explicitly list, but I kind of ruled out as I went here. So when I went north, north, I didn't bother going north again because I know that it already exceeds the amount. So there's a case for an error case, basically. When it exceeds an amount, or if I had gone north, north, east, east, I wouldn't bother because I already know it's gone past my amount. If I'd gone north, east, east, I wouldn't have done that because it's going to go past the eastern border. So there's an error case when it's already failed, or a fail case, I should say. And then the recursive case, so instead of doing like 2 times level 1, we're going to instead look at recursion going kind of in a forward way. So from here, you notice that what I did is each time is I tried to be logical about it. I tried to go north first. So I'm always trying to go north, and then I'm going to try to go north, and then, oh, I can't go north anymore. So now let's go east. And then I tried going north, and then let's go east, and then I can't go any more east, so let's go north. So what I'm trying to do is actually try to go as north as much as I can first, and then I'm trying to go as east as much as I can. So I did the east, and then north, north, and then went the north, east, and the north. And then the third thing I'm trying these northeast paths, okay? And so the recursive case is that you want to try from whatever point you're at. Let's say you're at this point here. You want to try going north, you want to try going east, and you want to try going northeast, okay? And then you add that onto the path. So when you're here, you're going to go try and going north. Nope. You're going to try going east. Yeah, that'll work. Northeast. Nope, that's not going to work. So let's take a look at a tree of these calls now. I think it's always good when you're designing code to draw out so you can visually see what it is you need to do. Not only so you can figure out what's going on, but then when you're writing the code, you can actually refer back to your drawings and see what it is at each level. So for example, at this level, let's walk through it first of all. So you start at 0, 0, And the way this works is we're going to traverse this, start going over to the left. So we're going to go to the north. So we start at 0, 0. North means we go 0, 1. And then we're going to try going east. So that becomes 1, 0 for 1 for the x and 0 for the y. And then we're going to try going northeast. So 1, 1. And then we recursively try the next level. So from here, we try going north. So that's 0, 2. And then we try going east. So that's 1, 1. And then we try going northeast, 1, 2. And then from here, we try going recursively to north, 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 to north, northeast, to north, northeast. And then when we actually look at these paths, we can see that this one has gone too far, this one is correct, this one has gone too far, so we don't need to do any more on any of these three. We had looked at these ones previously, so this one is going to go north, and it finds that this is correct, finds that this is too far, finds that this is too far. This one here is correct, so when you're correct, you stop, okay? And then we have to recursively go down the rest of this tree, and this will find all 5. So this is the kind of thing you want to draw out so you know that at each level. So let's talk about the code now. So what's the base case? The base case are actually these end nodes here. So when the path is equal to where you're trying to get, 1, 2, then that's the success case. The other base case is the failure case. So when the x or y has exceeded the goals that you're trying to reach, then that's a failure and you don't need to go any farther. If it's not a success and it's not a failure, then at each level what you need to do is try going north, try going east, and try going northeast. Okay, so those are the 3 things that we're going to actually try to put into code. This is code that has actually been provided by the book, and I'm going to talk about first something that came up in, I think it's section 12.3, and that is using a helper function. So sometimes you can do recursion with just the function itself. So here's the function that we're really trying to write, travel x, y. But sometimes you need extra information to be passed around. In particular, think back to what we were just going over, and I mentioned how when we reach the destination, that's when we're going to print the path. Okay, so in a simpler recursion case, the base case revolves around getting to 0, right? Like the x would get to 0 or something. But in this case, where x is actually going up. So we have to have a way to stop. So in order to do that, we're actually going to need to pass in extra parameters. So in addition to the target x and y, we're going to have the current x and y so that we can tell when we're actually going to be able to stop, when we've gone too far. And then we're also passing in a string so that we can actually track what the path is so far. So this is what's called a helper function. Anytime you're always welcome to use a helper function. Sometimes it's necessary, sometimes it's not. Okay, so we talked about 3 cases. We talked about how if we reach the destination, we have to print the path. If we've gone too far, we're going to have to return backtrack. And otherwise, we're going to recursively explore going north and northeast. So let's explore a little bit more. How do we tell if we've reached the destination? Right? What that means is cur x equals target x, and cur y equals target y. Right? That's gonna be how we can tell that we've reached our destination. Now, how do we tell if we've gone too far? Well, if the current x has exceeded the target x, not and, but or, the current y has exceeded the target y, then we've gone too far. Okay, and then otherwise we're going to recursively explore by going north, northeast, and northeast. So how do we do that? We're going to have to call travel with the same target x, target y, right? The targets never change. The current, however, may increase. The y may increase, depending on which direction we're heading. And then the path, we're going to add either north or east or northeast. Okay? So now let's actually write the code. So if, let's just copy this, current, if it's equal to that, then we just do a print of the path. And we can get rid of this now. And then if we've gone too far, so if current is greater than that, we just need to return. We don't need to do anything. And then lastly, how are we going to do this? So we're going to have 3 calls actually. So let's make 3 calls first of all. Oops. Fix that indentation. Oh, it's it's because I didn't close the thing. That's why. Okay. So we're going to do north first. So if we're going north, that means that our x is going to stay the same, and our y is going to increase by 1. And in this case, we're going to go north, and we need a space before that. Okay, so that's north. Then east. So east, the x actually increases by 1, and the y doesn't increase. And then the path is going to be east. And then northeast, both of these are going to increase. Okay, so let's do a simple example in our heads here of, let's say the target is 0, 0. Okay, if we do 0, 0, this is all zeros. If it's equal, then it just prints out the path. Okay, and that's it. It's not even going to call anything recursively. Let's say that it's 1, 0. Okay, so then it's going to come in here. It's 1, 0, so it's not equal. If it's greater than the target is x is 1. This will be 0. So 0 is not greater than 1. Well, the target is going to be, I'm getting a little confused, 0. So 0 is not greater than 0. So this isn't going to happen. Instead, what we're going to do is we're going to call travel again. So I think I said x is going to be, we're going to try going to 1, 0. So the first thing it's going to do is it's going to use the same x, and it is going to go 1 here. That's not going to work. But when we do this one here, it's going to go 1, 0. So then when we call this again, this will equal, and this will equal, and then it'll print that out. In the case where it's gone too far, so when y became 1, then the current y will equal 1, whereas the target is equal to 0, so it's going to fail there. So let's debug it. Let's debug it and see what happens. Set the debugger right there. Step into the debugger. Okay, so let's give it xy of 1, 0. It drops into the debugger here. We're just about to call it. It's going to call it again. Okay, so first it's going to check whether those x and y's are equal. I just brought the variables window up here so we can keep an eye on that. So it's going to check if anything's too far, and then we're going to be calling travel. So let's go ahead and recurse into this. So first it's going to add 1 to the y. So now you can see that the current y is 1 and the target y is 0. So guess what's going to happen? It's not going to succeed, but it is going to fail. It's going to return. Okay, so now we're on the second one. So let's jump into that. So now it's calling it with target 1, 0, and the current is 1, 0. So this should match. So it does print. This moves east. And then let's check. It's going to try to recurse again, all three of these are going to fail because we've already hit what we wanted to hit. So one thing we could say here is that when we've already hit the path, we should really be returning, right? So let me go ahead and stop. No, yeah, let's go ahead and stop this. All right, so I've added a return statement after we print out, so this will hopefully work a little better. Let's try debugging again. Let's go into 1, 0. We're going to step in. So we did the north already. And then the east, that's where we stepped in and we just printed out. So now we're going to return immediately. And that's going to do the northeast. So we're going to call into it with now 1, 1. Okay, and we're going to see that it's gone too far. We're going to return. Okay, and then we're done. So that's a sample execution of one run. Let's see, what else is interesting about this problem? So what we've learned in this example is recursive backtracking. So we've learned that unlike regular simple recursion problems, in these recursion problems, we're actually increasing complexity. We're going from a very simple problem to a more complicated problem. We're going forward, and instead of trying to count down until we hit a base case of n equals 1 or 0, we're actually counting up until we have exceeded some goals. In order to pass those goals, we had to use a helper method. So not only do we pass target x and target y, we also pass where we currently are, so we can compare from where we currently are to where we're trying to get. And we also pass a string or something to show what we've done so far, okay? So these are all useful concepts that apply to multiple recursive backtracking programs. And then in the code itself for the main function, just like before, we have to figure out some base cases and a recursive case. They're a little bit different though. So the base cases, when we have to look for reaching the destination or getting the right answer. Okay, and that's why we end up using both sets of input parameters. And we have to check if we've gone too far. And if we're just going to return. And then otherwise, you're going to recursively explore. In this case, you've got 3 different options to explore, northeast and northeast. Now, I wanted to point out that the book actually has a slightly different solution for this. It's slightly different only in that they took this backtracking case and they merged it here. And they just said, if not this, then do this. I keep them separate just so that it's very clear. In some cases, the comparison here may be very complicated, and so then it just makes everything else look more complicated. The two solutions are equivalent though. Also, I wanted to get clear on terminology. So backtracking only refers to the case where it has gone wrong and we need to retrace our steps and continue on. It's not generally used for the case where it's actually successful. You don't really see very much of that in the steps here, but in general, things are not necessarily this ordered when you do a recursive backtracking problem. You could have all sorts of chaotic things going on in here, and it's only when you realize that something isn't going to work out. Let's say you're playing chess, okay? It's not clear in chess that you've gone too far, quote unquote. So it's just at some point the evaluation becomes that this is no longer looking like a winning strategy. That's when you have to recursively backtrack. You're going to give up on this way and you're going to go back and try some other way. Okay, now that I've talked to you about the traveling northeast problem, I want to give you a problem of my own. So this is a function that I wrote called factors of n. And the simple idea is that you're going to factor a number like 8. So we all know that numbers are composed of prime numbers and non-prime numbers. So 8 can be composed of 1 times 8, 2 times 4, 4 times 2, 2 times 2 times 2. We're going to exclude the 1 times 8 just because if we used 1, there would be an infinite number of factorizations where it would be 1 times 8, 1 times 1 times 8, 1 times 1 times 1 times 8, etc. Thinking about the traveling northeast problem, that's why we always insisted that we traveled north or east, never south or west, because if we did, then we'd have a whole bunch of crazy loops, okay? So in these recursion problems, we want to make sure we're always progressing towards something. And So this is a simple example here. Another example is 35 is you've just got 5 and 7 or 7 and 5. So we want to have this be the function, but just like last time where I was saying you sometimes need helper functions, we're going to need a helper function in this case too. Just like in the traveling northeast, we need a couple of helpers because we're not counting down from n to 0 like we might be for factorial. We're counting up. So we want to count up towards n, 8 for example. So we want to start with small numbers and pass around 8 so that when we know that when we've exceeded the factors of 8, then we are going to stop. And we're also going to want to pass around, just like in the traveling northeast, we want to pass around these strings here of what it is we've done so far so that we can print that out eventually. So let's take a look at what the helper function should look like. So here's what the helper function should look like. It's going to be factors of, there's an n just like we had before, but I'm also going to include a product, which is, well, let's first talk about the string. The string result is what we've built so far. So it's going to start out with 2, and then we're going to have 2 times 2, 2 times 2 times 5. I didn't really talk about how we determine the factors, so the way we're going to determine the factors is we're going to start out with 2, and then we're going to multiply increment from 2 all the way up to n minus 1. So in the factors of 8, we're going to go try 2, 3, 4, 5, 6, 7 as all factors. And then product is the value of this string. It's really not necessary, but it would be wasteful to have to recompute this each time when we already have computed it in the past. All right, so let's take a look at a detailed call listing. This is kind of similar to that pretty picture that we saw for traveling northeast, except instead of graphics, it's in text. So it's originally going to be called with factors of 8. Then we need to call a helper function. So we're going to need a string, which will start out with being the identity string null. We're going to need a product, which we're going to pass the identity product 1, and then we're going to pass the number. Okay. Now the real work begins. So the first call we're going to generate. So these are the calls that are generated by this call. So this call, it's going to first check the base cases. Is it too far? No, because the product is only 1 and we haven't reached 8. Is it the right answer? No, because again 1 doesn't equal 8. So instead we need to iterate all the different factors from 2 to n. So 2, 3, 4, 5, 6, 7. And we're going to append that to the string we have. So that's why it becomes 2, 3, whatever up to 7. And then we're going to pass in the product, which is again just that number, the identity 1 times the number that we're passing in. And we're going to call each of those. So now let's take this first call here, 228. So the first, that 228 is then going to generate a bunch of further calls. So similar to the traveling northeast, where we would travel, let's say, north first, and then we would try to travel north again. So here we've tried 2, and we're going to try 2 again. So we're going to just append on 2, 3, here's 3, 4, all the way up to 7. Okay, so it's going to be a string of 2 items. So we take the product so far, 2, and we multiply it by the factor that we're looking at, 2. So that gives us 4, we call it. Here we take 2 times the factor 3. So this product is 6. So basically the number and the string always correspond to each other. Okay, so we're going to call all of those. Now we're not going to go down this road much, but I just want to point out when we make this call. Okay, so when this call is made, it's going to first check to see have we gone too far, and it'll say no, it hasn't gone too far because 8's not greater in excess of the product we're looking for. And it's going to check, is it equal? It is. So at that point, it's going to be successful and it's going to print that out. And then all the other, well, not all the, this one here, when it hits 7, it's going to pass 14, and the first thing it'll do is check to see, well, is 14 greater than 8? It is. So then we're just going to backtrack and try other more successful ways. And then I wanted to show another level. So this call here will generate this call. So it comes in with 2 and 2. It's going to use 2 as another factor. So 2 times 2 times 2. That will have a product of 8, and when it makes its call, it will determine that it will be successful. And so we get all the way down here until we're using 7 as the first factor, and then it's going to be calling 7.2, 7.3, 7.4, etc. All right, so that's a model for how that's going to be called. So I've given a number of hints and requirements. The ones I want to focus on are the instructions for how to determine the 3 cases, okay? So you're going to need a dead end or a backtracking case. And so remember what we talked about, when do we know that we need to backtrack? That's because eventually you get products 2 times 2, 2 times 3, 2 times 4. Eventually it'll be too big, it'll be 2 times 7. And that's bigger than the number we want to factor, which is going to be in example 8. Okay, so when that product is greater than the factor that we're looking for, then the number that we're trying to factor, then we need to stop. We're not going to print anything, we're just going to stop, we're going to return. Okay. Second case is, what's the success case? So that means that the products that we're passing in, there's going to be a string of 2, 2, 2, and a product of 8 is equal to the number that we're looking to factor. Okay, when it is, then what we want to do is we want to print out, and I'm suggesting here factorization equals with the number in these brackets. So that's going to print out factorization, and then it's going to return. Okay. And then the third important case is, what is the recursive code? So remember in traveling northeast that we had 3 things to call. We had to travel an additional step north, a step east, and a step northeast. Here we have an almost unlimited number of calls that we may need to make. We need to make the call for all factors between 2 and n. So we're going to have to write a loop between that 2 and excluding n, so up to n minus 1. And there's some details here about how you want to format it. It's not as important as just making sure you're going to have to do a loop calling with, you're going to have to append the next factor. So 2 and 2, you're going to have to append it. It'll actually be with a space. And you're going to have to multiply the product. Okay, and one mistake that some students make is they think, okay, well, I'm actually going to change what the string is to be 2 space 2. And you don't want to do that because you're in a loop. You're going to need that string. So instead, just call it with 2 and then concatenate on the string space 2. Okay, and similarly for the product, you don't actually want to change the product. You just want to pass in as a parameter n times whatever the current factor is, 2. And then you're not going to do anything to the n, right? Because n is always the same. So that's the set of recursive calls you're going to make. And then if you do that all right, you should get a recursive call tree that looks like this. Okay? So again, it's always good to look at your diagram and see what do you have to do. So from this function here, you need to add on space 2. You need to add on space 3. You need to add on space 4. And you're going from the product of 2. You're making it 2 times 2, 2 times 3, 2 times 4, and then n, you're keeping it the same. So it's similar to the traveling northeast problem, but not quite. But you're using the exact same strategy of how to do the traveling northeast problem to solve this factors of problem. Section 12.6 of the book has another example. And this is called Prefix Evaluator. And Prefix Evaluator is not it's not a recursive backtracking situation. We're not generating a whole bunch of cases. It's a straightforward evaluation. First, let me talk to you about what prefix notation is and what Prefix Evaluator does. So there are 3 different ways to evaluate math expressions. The one that we're used to is referred to as infix notation, where we have operators separated in the middle by the operands, 1 and 2, separated in the middle by the operator, plus. Prefix notation is if you move the operator to be before the operands. So we have plus, 1, 2. And then postfix is where you put the operator afterwards. It's also called reverse Polish. Then it would be operator 1, operator 2, and then plus. So why they choose to do the prefix notation is really, it's an artifact of this becomes very easy to do for recursion. And we'll go into that, why. I actually have another problem set for my students where I ask them to do the postfix or the reverse Polish notation. And I use stack for that, because that really lends itself very well and very easily to doing stack operations. So and so that's going to, a lot of this code will apply, but it's going to be a different operation. So first, let's take some examples here. So plus 1, 2. You see the plus operator, so you know you're looking for two operands. So you see an operand here, and then you just add them up. Similarly, minus 5, 4, you would take 5 minus 4 is 1. Okay, let's go to a nested situation. So here you have the operator divide. So now you know that you're looking for two operands, okay? But you're gonna need to recursively call to get the value of this expression here. So when you recursively call this expression, it's going to say, okay, well, I've got a plus and I've got a 1 and a 2. I know how to do that. So this is really the base case when you have just a simple operator and two operands. The recursive case is where you've got, it's not simple. You've got a full expression. So this divide, you have to recursively evaluate this expression. You have to recursively evaluate this expression. That ends up with the divide 3 divided by 1, you get the result of 3. Here's a triply nested situation. So we got plus, we know we're looking for two operands. One of the operands, one of the operands is going to be here, this big expression here, and then the other operand is just off in here. So let's recursively look at this. So how do we evaluate this? We got a minus, and so we know we've got two operators we're looking for. This is one of the operands, and this is the other operand. And then we have to recursively go down to here. This becomes 3, that becomes 1, and so then 3, I'm getting confused, 3 and 4 minus 3 is 1, so that's 4, okay. 3 and 1 and 5. So then it's doing subtract on the 3 and the 1 becomes 2. The 5 still remains, and finally the top level 2 plus 5 is equal to 7. All right, let's take a look at what this code really looks like. So first we've got just a main here. It's going to give some simple introduction, and then we're going to do the it's going to ask for the expression. That's important, and then it's going to do the evaluation. Okay, so it's a little bit confusing because it's scanning instead of using the string, but it's all the same. So if the input has a next double, it's going to return the double. That's really the base case. So when you've just got a number, you're just going to return that number. Otherwise, it's going to be, this is a recursive case. So you're going to get the has next double. So it didn't actually scan it yet. Here's where it scans it. So if it doesn't have a next double, then it believes that the next one is going to be an operator. So it gets the operator, and then it has to call evaluate on the input, and then finally evaluate on the entire expression. And notice that evaluate is overloaded. So here evaluate's taking the scanner, and here evaluate is taking the full expression. So I misspoke earlier when I was saying the base case is really like plus 1, 2. The base case is really when you get down to one level further, when you get to 1. Okay, that's when the base case, we know what to do with 1, we just return it. Okay. So here in evaluate, it's just going to take a look at the operand. If it's plus, minus, times, divide, mod, it's just going to apply those operators. And reverse Polish notation similarly needs a way to evaluate whether this character is going to be any of these operands. So it's a little bit similar to that. So we've got the base case and we've got the recursive case here. So let's go ahead and run it. Let's do the simple case. So plus 1, 2. Oops. Okay, that's 3. Let's run it again. So now minus 5, 4. That should be 1. We've got a more complex expression down here. That's value 3. And then we've got this very complex expression here. And that is 7. And I wonder if it would be worth, well, let's go ahead and step into it with the debugger and just have a quick look here. So let's set a breakpoint right there. Step in the debugger. Let's give it that complex expression again. And let's see, where are we in the debugger? No, it didn't work. Let's try that again. Oh, so I think I ran. No, I did debug it. Okay, hit the debugger, give it the expression. All right, so if it's first it's checking if the input has an x double. So that's going to be looking at the plus, so it's going to be false. So instead, it's going to get the operator. And so we can see the operator was the plus. And then it's going to get the operand. Let's go ahead and step into this. So it's going to similarly get the operator, which is now the, let's go back to the console. The operator is now going to be the minus. And it's going to step into evaluate again. And once again, it's going to get the operator. And then again, the operator is going to be plus. And then finally, we're going to start to see the 1, the 2. So we're going to step into it one more time. Now it isn't double, so it's returning that double. So that's the first operand. You can see operand is 1.0. We're going to step into this, and it's going to see the double of 2 here. So it just returned 2. You can see the operand 2. And now it's going to call evaluate, which is going to step down in here, and it's going to add 1 and 2, which will be 3. Okay, so that is, let's take a look at the call trace here. So you can see that we've nested our calls here. We're in a second level of recursion because we're not done. So what we did is we just evaluated this part here, and it returned 3. But now I believe the operator is a negative, minus, right? And so now it's going to be scanning this part here, the minus 4, 3. So let's go ahead and look into that. We're going to evaluate this. And the operand is equal to 3. And now it's going to step into evaluate again. So now this is operator minus. I believe the first one is going to be a 5. Yes, operand 4. And then the second one is going to be a double, which is an operand of 3. And now it's going to, we'll step over this, so that'll result in a value of 1 for the operand 2. Okay, so it just returned this operand 2. So if we could look at the console, so it just did this. And so now it's got operand 1 is 3, operand 2 is 1. The operator is minus. So it's just about to do this expression here now. So it's going to do minus 3 minus 1. Step into it. It's going to go down to negative, subtract, and then it's going to return 3 minus 1. So that's going to be 2. And now it's going to store that 2 as operand 1. So right there. So this entire expression just evaluated to 2 as the first operand. The second operand is just a 5. So when we evaluate this, it's going to see a double. It's going to return that 5, sure enough. And then we're going to evaluate the 2, is it plus? Yeah, 2 plus 5. So we're going to step into plus. We're going to return 7. And now that's the end, 7.0. So that's how you do the prefix evaluator. So doing the RPN evaluator really requires a discussion about stacks. So that'll be in the stacks lecture, but it's somewhat of a similar thing, except that instead of using recursion, we're going to use stacks. And the truth is that recursion actually does use stacks. Recursion uses the computer's call stack. Every time you recurse, you're actually putting information onto the stack. But using stacks as a data structure formalizes that, and it's a more efficient way of doing it. Okay, so let's talk about what did we cover in this video. So we covered 2 major topics. One is recursive backtracking, like the go northeast problem. Recursive backtracking, unlike simple recursion, you're typically recursing more complex, and because you're going more complex, you're going to need a helper function so that you can track not only where you are, but where you're heading to. And you have to be able to stop yourself from going too far. You have to be able to stop yourself when you get to the right place, and then you have to recursively explore a number of options. I also talked about the factors of problem, which has the same type of things, except that instead of having a fixed north and east and northeast directions, you have to add on a whole host of factors from 2 till n-1, and then you need to check whether you already whether you've hit n and whether you've exceeded n for those other recursive backtracking cases. There's other couple great recursive backtracking cases, one called the 8 queens problem. There's also a Sudoku recursive backtracking problem. Those are great examples in the book. The second topic we talked about was prefix evaluators. So this is the recursive form of prefix evaluation with the, we're doing it prefix so that when we see an operator, we can then recurse on getting the two operands. Okay. When we hit stacks and queues, we're going to take a look at an iterative way of doing postfix notation using a stack instead. All right, so that covers the entire topic of recursion. Hopefully you've gotten some appreciation for what kind of problems are useful for recursion. They can solve problems that are difficult to see the solution from, for looking at trying to look at the solution easily, but you can solve a simple problem, and you can use recursion to solve larger and larger and larger problems. So sometimes recursion is going to be an advantage. That concludes the recursion topic. Please like and subscribe to the channel. Next week we're going to be hitting up stacks and queues. And if you haven't reviewed any of these other topics, please go back and feel free to review them. Thank you very much.